Welcome to This Explainer. Today, we are diving into a highly engineered, extreme environment device that literally turns chemistry into motion. It's small, it's completely unassuming, but without it, well, most cars on the road today simply wouldn't move. Yep, we're talking about the spark plug. Just think about this for a second. How can a tiny little spark inside a super hot, pressurized engine cylinder ignite a mixture powerful enough to push a massive metal piston and propel a 2-ton car down the highway? I mean, it feels almost like magic, right? But as you'll see, it is pure, precise engineering. Okay, before we get too far ahead of ourselves, let's clarify exactly what a spark plug actually is. Basically, it's an electrical device that provides a perfectly controlled ignition spark inside the combustion chamber. Its primary job? To initiate combustion. It doesn't create the fuel-air mixture, and it certainly doesn't compress it. It just acts as the ultimate catalyst, providing the exact amount of energy at the exact right microsecond to kick off that chemical reaction.
So here's our roadmap for today's explainer. We're going to start with the anatomy and the engine cycle, then explore creating the plasma spark, how it survives the brutal engine cylinder, debunk some common myths, and finally, trace the whole cycle from spark to motion.
Let's kick things off with Section 1, Anatomy and the Engine Cycle. Let's see where our hero actually lives, inside a moving vehicle. Right, so to really get the spark plug, we gotta understand its neighborhood, the classic 4-stroke gasoline engine cycle. First, you have the intake stroke, drawing in air and fuel. Then, compression, where the piston moves up, tightly squeezing that mixture. Now, here is where it gets super interesting. Near the end of this compression stroke, usually just before the piston reaches its absolute highest point, the ignition system tells the spark plug to fire. This kicks off the power stroke. You might be wondering, why fire before the top? Because combustion is an instant. It actually takes a tiny bit of time to develop the high-pressure gases needed to push the piston down. And finally, the exhaust stroke pushes all the spent gases out. Let's zoom in a bit on the anatomy to see how this thing handles such a crazy environment. Up at the top, you've got the terminal connecting to the ignition system. Then, the central electrode carries that high voltage straight down the middle. Notice the ceramic insulator there? It's usually made of some incredibly tough alumina, and it perfectly isolates the central electrode from the threaded metal shell on the outside. That shell gives it mechanical strength and grounds the plug to the engine block. Because of that tough ceramic insulator, the electricity literally has nowhere else to go but down, jumping right across the spark gap to the ground electrode at the very bottom.
And you know, this perfectly illustrates why engineers absolutely obsess over materials. We hear a lot about conventional nickel alloy versus precious metals like platinum or iridium. Using iridium isn't just some magic trick to add horsepower. Actually, these materials are incredibly resistant to high temperature wear and erosion, which means the electrode can be made much, much thinner. This fine wire design helps concentrate the electric field and actually lowers the voltage needed to initiate a spark, all while massively improving how long the plug lasts.
Moving right along to Section 2, creating the plasma spark. This is all about microsecond timing. Let's break down this timeline, zooming in extremely close to the microscopic physics. It actually starts outside the spark plug, over in the ignition coil. When the engine's computer cuts the current to the coil, its magnetic field rapidly collapses. Boom! Electromagnetic induction generates tens of thousands of volts. This massive surge of voltage is sent straight to the plug's central electrode. Now, normally, that compressed gas mixture in the gap acts as an insulator, blocking electricity. But as that electric field strengthens, it simply overpowers the gas. The gas breaks down, electrons accelerate and smash into molecules, and in literally a microsecond, a highly conductive plasma channel forms. Only then does the actual flame kernel develop. Okay, if you take away one thing today, make it this. The spark is not just electricity jumping through empty air. It is a rapidly developing electrical discharge through an ionized gas. We're looking at a localized microsecond electrical breakdown. That initial incredibly hot ignition region, the flame kernel, then grows outward into a propagating flame front that steadily consumes the whole combustible mixture. Up next, Section 3, surviving the engine cylinder. Let's look at the brutal heat and pressure these things face. These plugs operate in an absolute inferno of high combustion pressure, extreme temperatures, violent mechanical vibration, and nasty chemical exposure. So how do they survive? Engineers use this brilliant concept called heat range.
It doesn't mean the maximum temperature the plug can endure. Instead, it describes how effectively the spark plug transfers heat away from its firing end and into the cylinder head to cool off. A hot plug holds on to more heat at the tip, which actually helps burn off carbon deposits. A cold plug transfers heat away much faster. It is absolutely crucial that this heat range perfectly matches your specific engine. If it doesn't, you either get fouling from being too cold or dangerous overheating from being too hot. But what happens if that heat management goes wrong? Well, if a plug gets way too hot, it turns into a glowing hot spot and causes something called pre-ignition. This is exactly what it sounds like. Combustion begins before the intended spark event even happens. Now, people mix this up with engine knock or detonation all the time, but they are completely different. Knock involves abnormal, super rapid pressure oscillations because the mixture auto-ignites after normal flame propagation has already started. They are different for sure, but both are severe abnormal conditions that can totally wreck an engine. Look, nothing lasts forever, right? Over time, that intense environment just eats away at the electrode. The spark gap literally widens, and a wider gap means the ignition system has to work way harder to force a spark across it. Plus, plugs can get completely fouled up. You can get carbon fouling from incomplete combustion, oil fouling if worn piston rings let engine oil slip in, or fuel fouling if the engine is running way too rich. These physical issues lead to real-world symptoms you will absolutely feel behind the wheel, like engine misfires, a super rough idle, hard starts, or your gas mileage just tanking. All right, section 4, common spark plug myths. Now that we've got a grip on the science, let's separate some fact from fiction. First up, the classic diesel mix-up. People constantly confuse spark plugs with diesel glow plugs, but honestly, they are completely different animals. Gasoline engines need spark plugs to create an electrical spark to start combustion. A conventional diesel engine, it doesn't even have a spark plug. Diesel relies purely on extreme compression to heat the air so much that the fuel just ignites the moment it's injected. Glow plugs in a diesel are basically just tiny little heaters that provide a little extra warmth to help out when the engine is cold. They absolutely do not spark. Let's knock out a few more of these pervasive myths. Myth 1, the spark plug creates a massive explosion. Reality? It merely initiates combustion. The chemical energy is released as the flame spreads. It doesn't instantly detonate all the fuel at once. Myth 2, more voltage equals more power. Reality? The engine just needs enough voltage to bridge the gap. Dumping a bunch of excessive voltage in there does absolutely nothing to automatically give you more horsepower. And myth 3, a colder plug gives you more performance. As we just learned, throwing a colder plug into an engine that wasn't designed for it, that's just going to cause carbon fouling. The heat range has to perfectly match the engine.
And that brings us to our final act, section 5, from spark to motion, the complete cycle.
What is just absolutely wild here is the sheer speed of this whole sequence. It starts with a digital signal from the engine's computer, commanding the ignition coil. High voltage instantly hits the spark gap. The gas yields and a plasma channel forms. A flame kernel ignites and rapidly spreads through the compressed air-fuel mixture. The chemical energy releases, creating highly pressurized expanding gases. Those gases violently shove the piston downward, and that straight linear motion is beautifully translated by the connecting rod into the rotational force of the crankshaft. It is a digital computer command perfectly bridged into raw mechanical muscle. I want to leave you with this thought today. Every time a gasoline engine comes to life, thousands of tiny electrical events help turn chemistry into motion. And at the center of each one is a spark plug. It's incredible to think about this invisible, highly controlled chaos happening under the hood, thousands of times every single minute you're driving. It definitely gives us a profound appreciation for this tiny piece of ceramic and metal. So, what other hidden automotive marvels are silently powering our lives right under our noses? Thank you so much for joining me on this explainer. Keep wondering how things work, and we'll catch you on the next one.